So let's talk about one of the most important concepts in all of thermodynamics, which is the inequality of Clausius. First, let's just make sure we're clear on some definitions when we're talking about heat engines. When we say a heat engine, what we mean is some device, here, heat engine, it accepts some heat, which we're going to call QH, from some high temperature source, TH. So here's our high temperature source, it's just a thermal reservoir at some temperature, and it's transferring an amount of heat, QH, to our heat engine. The heat engine is going to use some of this heat input to produce an amount of work, W. Here we're not worried about the specific processes that the heat engine is using to convert some of that heat into a net work output. We're just looking at it at a more system level. The second law of thermodynamics tells us, specifically the Kelvin-Planck statement of the second law of thermodynamics, that we can't turn all of that heat input, QH, into work, W. So to be a heat engine that satisfies the second law of thermodynamics, it must reject the remaining heat that it did not use to some low temperature sink at a temperature that we'll call TL for low temperature. So this is what a heat engine does. Takes some heat from a high temperature source, turns some of it into work, and then rejects all the heat that it couldn't use to some low temperature sink. And the other thing that must be satisfied for it to be a heat engine is it has to do this in a cyclical manner. And if something's running in a cycle, that means it's returning to its original state. So we're not accumulating energy inside our heat engine here. As we run in a cycle, we bring in some heat, we turn some of it to work, we reject all of the heat that we did not use to our low temperature sink. Since we're running in a cycle, and as we've said, that means that the energy stored inside the heat engine system cannot be changing, the first law of thermodynamics then allows us to specify that the amount of work produced must be equal to the difference between the amount of heat that went in and the amount of heat that came out. Now here we're going to introduce a concept called cyclic integrals. And really mathematically, what this means is it's a line integral along a closed path. And if you want to refresh your memory on line integrals, you can start on Wikipedia, which has provided this little animation here on the right to sort of illustrate what we're talking about when we talk about a line integral. The example here is not for a closed path. In thermodynamics, when we say a cyclic integral, we mean an integration performed over the paths that make up a cycle. Now, calling it a cyclic integral is really something that we only do in thermodynamics. If you want to look at the mathematical basis of it, this is just a line integral along a closed path. Let's look at an example of how we might formulate a cyclic integral. And here we're going to use the most fundamental of all thermodynamic cycles, the Carnot cycle, with its two isothermal and two isentropic processes. So what would we say that the cyclic integral of heat transfer is in this case? Well, we'll start with our process that takes us from state 1 to state 2, which is our isothermal heat input, and we'll say that some amount of heat transfer occurs between state 1 and state 2. Now for any little increment along our path, there will be some amount of heat transfer taking place, delta Q. And by integrating along this entire segment between points 1 and 2, we will get the total heat transfer associated with this particular process. We then have our process as we move from 2 to 3. So we add the heat transfer associated with that process. Then likewise, we integrate along our path from 3 to 4, and we have the total amount of heat transfer that takes place during that process. And then lastly, to return to our original state, we integrate the heat transfer that takes place between 4 and 1 to get us the total heat transfer that's taken place during this process. Now, of course, in the Carnot cycle, there's only heat transfer during two of these stages, the isothermal heat input between state 1 and 2, and the isothermal heat rejection between state 3 and 4. And this is equal to all of the heat transfer from a high temperature reservoir minus all of the heat transfer out to some low temperature reservoir. So we see our cyclic integral here is just the difference between all of the heat input QH and all of the heat output QL. Now it's important to remember that the Carnot cycle is just one example of a heat engine cycle. There are many others, but whether we're talking about the Carnot cycle or something based on the Otto cycle or the Brayton cycle, we can always just represent it in this general system level form. Any heat engine can be represented as an amount of heat input producing some amount of work and rejecting some amount of heat. And we're going to stick with this general sort of system level form of the heat engine for the rest of this discussion. So we saw for the example of the Carnot cycle that the cyclic integral of the heat transfer was just the difference between the heat input and the heat output. But hopefully we can see here that this is a general statement for any heat engine. There's more heat going in than going out. So the cyclic integral of the heat transfer is just the heat input minus the heat output. So now for us to develop the inequality of Clausius, there's many different ways that we can do this derivation, but the one I prefer is based on Carnot's principles. So as a quick reminder, though we're not covering it in detail here, what Carnot's two principles tell us is that if we have temperature reservoirs at TH and TL, and if we set up an irreversible heat engine between them, and then a reversible heat engine between them, any reversible heat engine will have a greater thermal efficiency than any irreversible heat engine running between these two reservoirs. So that's the first Carnot principle, and we're going to make use of that in just a moment. The second Carnot principle tells us that any two reversible heat engine cycles running between the same temperature reservoirs will have the same thermal efficiency. And we're going to make use of this one in our definition of thermodynamic temperature. And we need really both of the Carnot principles for our development of the inequality of Clausius. So from the second Carnot principle, we get our definition of thermodynamic temperature. It is a non-empirical, but rather a theoretical temperature defined by the ratio of heat transfers that happen between thermal reservoirs for a reversible heat engine cycle. To develop the Clausius inequality, we'll consider two cases: all reversible heat engines and then all irreversible heat engines. And between these two categories, we have all possible heat engines. First, let's consider the reversible case. Because we're considering a reversible heat engine, we can draw on our definition of thermodynamic temperature. The ratio of the heat input to the heat output is equal to the temperature at which those transfers are taking place. And again, this is only true for a reversible cycle. So let's rearrange this expression now, and instead say that for a reversible heat engine, the amount of heat transferred in divided by the temperature of the reservoir equals the amount of heat transferred out divided by the temperature of that reservoir. And we're going to be able to do something useful with the equation in this form. So here we have this idea of the heat transfer divided by the temperature at which that heat transfer is taking place. And we can express either heat input at the high temperature or the heat output at the low temperature as the integral of the inexact differential of the heat transfer divided by the temperature at which that heat transfer is taking place. With this so defined, we can now express this quantity as a cyclic integral. The cyclic integral of the inexact differential of heat transfer divided by the temperature, we can now express this quantity as a cyclic integral. And for any heat engine, the cyclic integral of the heat transfer divided by the temperature at which it takes place will be the heat input divided by the high temperature minus the heat output divided by the low temperature. And if we then combine this with the statement that we derived from our definition of thermodynamic temperature, we can see for our reversible heat engine, the cyclic integral of the heat transfer divided by temperature is equal to 0. This is the first half of the inequality of Clausius. This is the equality part of the inequality of Clausius. So there we have a statement for all reversible heat engines. Now, to cover the rest of our bases, we want to say something about irreversible heat engines. So the first Carnot principle tells us that the thermal efficiency of our irreversible engine must be lower than that of any reversible engine. Of course, as we already established from the first law of thermodynamics, the work output of any of these heat engines is equal to the difference between the heat input and the heat output. We can combine these two statements by reminding ourselves of our definition of thermal efficiency, which is the work produced by a heat engine divided by the required heat input. And here in our schematic on the right, we're using the prime to indicate that we're now talking about the quantity associated with the irreversible cycle as opposed to the reversible cycle. Now, if we're relying on the Carnot principles to compare irreversible and reversible heat engines, we have to be considering the same temperature reservoirs. So TH and TL are the same whether we're talking about our irreversible heat engine or our reversible heat engine. We also have to fix one of our inputs. So let's assume that both the irreversible and the reversible heat engine are receiving the same amount of heat, QH. So for the same amount of heat input, if the irreversible engine is less efficient than the reversible engine, that must mean it's producing less work output. So the work produced by the irreversible heat engine will be less than that produced by the reversible heat engine. From the first law of thermodynamics, then, a consequence of this is that the irreversible heat engine must reject more heat than the reversible heat engine. What does this mean for our cyclic integral? Well, in the reversible case, we saw from our definition of thermodynamic temperature that QH on TH was equal to QL on TL. Now, our TH and our TL are the same as they were before. Our QH is the same as it was before, but we are rejecting more heat in the irreversible case than the reversible case. So if QH on TH was equal to QL on TL before, and we've kept QH, TH, and TL the same, then the only possible outcome for the irreversible case is to say that QH on TH must be less than QL on TL. That means now, if we evaluate our cyclic integral, QH on TH minus QL on TL, which is the cyclic integral of the heat transfer divided by temperature for our irreversible engine, must be less than 0. So for all reversible heat engines, the cyclic integral is equal to 0. For all irreversible heat engines, it's less than 0. So here are those two results put side by side. If we then combine this into a single statement, we get the inequality of Clausius, the cyclic integral of heat transfer divided by the temperature at which it takes place is less than or equal to 0 for all possible heat engines, reversible and irreversible. So, there we have one of the many possible derivations of the inequality of Clausius. This one formulated based on the two Carnot principles. It's important to know where the inequality of Clausius comes from because it's going to be absolutely integral to our development of the concept of entropy. See you next time.